Before we move to next two examples, one thing, because we are in this slide, some information in this slide is needed. One is for case 2, R equals this, the relationship, okay? R equals that, So later I will refer to this formula, Another thing is case 3, when we get R1, R2, we need, because when you get two distinct roots, two roots, how do we arrange those two roots? So we use this. R1 should be greater than R2. R1 minus R2 is a positive number. All right, so later we will also use this. All right, let's start examples. B point, sorry. We finished. Oh yeah, remember to talk about Frobenius method. I get out, then I jump to So we need to jump. Okay, the next topic we need to jump. Otherwise we already complete the convergence part. We jump to B.5. Examples using Frobenius method. All right. Color change. Every time when I exit, I need to change the color. Pen color. All right. Let's look at these two examples. Case 2, case 3. Case 2, double root. Solution 1. Solution 1, the usual way. Solution 2, a different way. Let's look at the question first. Solve this ODE. Look at this ODE. You can see the coefficient for y double prime, y prime is a simple polynomial. All right. Then, in order to apply the Frobenius method, we need to change to the standard form, right? Because Frobenius method, there is a standard form to begin with. So first we need to go to that standard form. So what's that standard form? Divided by the coefficient of y double prime. So you make the coefficient of y double prime 1. That's the standard form. Because in the standard form, let me show the format of the standard. This is the format of the standard form. Okay. Because we need to use the power series representation for B of x and C of x. Power series representation. So now, we need to first C function. So let's take out C function. C function, because C function over x squared equals this function. So your C function, you should multiply that function by x squared. Okay. All right. After cancellation, it's x over x minus 1. Now the next question, how to find a power series representation of this function? Okay, power series representation. All right, this one is simple. Recall the geometric series. First, you write this way. Okay, you can take 1 out. All right, this way. The second, you write it as this form. Because if you are familiar with the geometric series, 1 over 1 minus x, this is corresponds to the geometric series. Okay, that simple geometric series. All right, there, that's the, that geometric series. And the convergence interval. The convergence interval. So within the convergence interval, you have this power series. Yeah, convergence interval. Right? Yeah, convergence. Yeah. Now, inside this interval, you can do a lot of operations. Yeah. So you don't worry about, converging or not. Yeah, because we do all our operations within this interval. All right. Second, we need to represent B of x. Yeah, based on this format, you need to multiply extra x. Yeah, one. This part, you need to multiply another x to it. This x. Cancellation, right? You have cancellation. 3x. Can you take 3 out? 3 out. Then, 3 minus 2 times that geometric series. Yeah. Then you simplify a little bit. Yeah. See. There. Can you see what is the convergence interval of that one? Convergence interval, although you can apply, theorem. Yeah. But here you can see, when you look at convergence, you just look at convergence interval here, right? Yeah. That's the, same convergence interval. Yeah, same convergence interval. Yeah. All right. So now, after we get power series representation for B function, C function, yeah. Next, initial equation, right? Lucas, any question?
I'm a little confused about, so we do the algebraic manipulation, we get 3x minus 1 over x minus 1
Mm-hmm.
equals 3 plus. Is it the same thing where you're just examining it and you're...
Right. This middle term, the same thing, same as that, right? Yeah. So you can make them equal. Then you try to find the B of x. Okay? You just multiply the denominator x to this whole thing. Yeah, that's the Vx. Yeah. This side, you make this, coefficient part the same as that part, C of x over x squared. Then you solve for C of x.
I'm
Yeah.
confused about the next step,
Next,
the 3 plus 2 over x minus 1.
this step, this step. All right. Yeah. Okay. Yeah. So usually people do this way. Yeah. So how to see that? Okay. Yeah. All right. 3x minus 1 over x minus 1. All right. You do long division. You know how to do long division, right? Yeah. 3 times x minus 1. Do you need 2 plus 2 over x minus 1? 3 times x. Yeah? Then you have 3 plus 2 over x minus 1. Yeah. On your scratch paper, you can do long division. Okay? Yeah. Yeah? So that kind of algebraic operation. Yeah. All right. Yeah. So let's move to the next step. Next step, we need to solve that initial equation. Yeah. Yeah. So here we, because to determine that R. So what is that R? Okay. Yeah. Here we use the extended power series method. Yeah. Yeah. The Frobenius method, we need to use extended power series method. Yeah. So we need to find that R. Yeah. All right. So here, if y takes this one, can you see? Yeah. So here, another big step. Yeah. Let me erase. I need some space. All right. So here, this step, I want to. Yeah. All right. Yeah. Y equals this one. Now you plug in this equation. You need to take y prime, y double prime. How do you get this whole thing, right? How do you get this whole thing? Yeah. So this one, this long formula, I cut it from the textbook. Okay. All right. But here I want to explain a little bit. All right. First, because when you take a derivative, here it's a product. This power function multiply power series. But if you use the product rule to take derivative, then it's too complicated. All right? So the simplest way, you do not apply the product rule. Okay? You can multiply through, multiply inside, right? Can you, it's x to the r, inside you combine with each x power term. Okay? Yeah. Yeah. So in that way, you can see y, this is the y. See? Yeah. The exponent becomes m plus r. That's the y. All right? Then when you take a derivative, it's easier, right? The derivative, yeah, this is the derivative. This is derivative. Okay? The power rule. Yeah. Term-wise, you apply power rule. That's the derivative. Okay? The second derivative, not the second derivative. Yeah. Second derivative, you apply another times. Yeah. So here, I like to multiply another times. Yeah. M equal to 0. M plus r. M plus r minus 1. am x to the m plus r minus 2. Yeah. Minus 2. Okay? All right. Then, this term, you do this way. Okay? Yeah. You split into two terms. X squared times y double prime minus x times y double prime. Yeah. Yeah. Otherwise, it's very messy. Yeah. So you want to separate the terms. Then x squared multiply y double prime. Look at it. You multiply x squared here. 2, so you cancel that minus 2. Okay? So you have m plus r, then this part. Okay? So this is for this first summation for x squared times y double prime. All right. Then the second summation, yeah, because this time you only have one x. Okay? So you minus 2 plus 1 becomes minus 1. M plus r minus 1. Then the coefficient part is the same as before. So this is for the x times y double prime. Okay? Yeah, the second summation. The third summation, yeah, so here, you use the same method. Yeah. 3x, 3 times, write them separated. 3 times x prime minus y prime. Okay? 3 times x prime, yeah, because derivative this one, you multiply by 1x here, you get a m plus r. And 3, okay? So this corresponds to 3x y prime, okay? This corresponds to y, because y prime, minus 1, okay? Then the last one. Okay, that's the way, yeah? You can do, otherwise, if you do not write separately term by term like this, then it could be very messy. Yeah, very, very messy. Yeah. All right, yeah. So now, after you understand this step, next, we need to, combine. Yeah, remember our property 4, vanishing, right? Vanishing in, power series, right? That property number 4. Yeah. Before we apply that, vanishing property, okay? Yeah, because both sides, left hand, right hand side 0. So the vanishing property, we compare the coefficient. The coefficient of each term must be 0. All right. So next, we need to calculate this initial equation. How to calculate initial equation? Yeah. Now let me explain. Okay. Yeah. I talked about that initial equation before, but I didn't explain how do we get this initial equation, right? Yeah. Here, let me explain how to get initial equation. Yeah. Here it's like this, but I explain how do we derive it. Yeah. All right. Let's look at the starting point of each summation, starting from 0, right? Yeah, starting from 0. Starting from 0. Starting from 0. Okay, yeah. Although starting from 0, yeah, let's consider what is the lowest term. Lowest degree term. Yeah. What is the lowest degree term? Okay. For each summation, for this summation, the lowest degree term, m equal to 0, m to the, a0, x to the r, right? Yeah, lowest degree term, yeah, for first summation. Second summation, where m equals 0, a0, x to the r minus 1, right? Yeah. Yeah, the leading part we will add later, okay? Yeah, so this one also, same as this one. Yeah, minus 1, same as that one. Yeah, this one, same as that one. But you compare these two, which one is lower? Yeah. Because we want to look at the lowest term. This is lower, right? R minus 1 lower than R. Okay, so let's focus on this term. Yeah. This, if we combine the coefficient for this term, we will get the initial equation. Okay, all right. So combine for this one, only 2 summations contribute to this term. Okay, yeah. Only these two, this summation and this summation, contribute to this term. Yeah. All right, let's look at the contribution from this summation. You plug in m equals 0, r negative. You have negative, right? You have negative r times r minus 1, a0. Right? Yeah. Right. Then contribution from this summation, yeah, m equals 0, you have r, right? But it also minus r a0, right? Yeah. Times x to the r minus 1. Yeah. By that vanishing property, this coefficient must be 0, right? Yeah, because the coefficient of each term must be 0. The coefficient of this term must be 0. Okay? That is this initial equation. Okay? Yeah. All right. That initial equation, because a0 is an arbitrary parameter, okay? Some parameter. Yeah. So we do not expect a0 to be 0. Yeah. So we can cancel out a0. So then you need to solve the quadratic equation, this quadratic equation. Okay? All right. So when you solve that quadratic after cancellation, what do you get? R squared equal to 0. You see? The quadratic equation becomes r squared equal to 0 is the double root of r. Okay? 0 is a double root. Yeah. Then I bring back that case 2 formula. Remember? Yeah. Before we came to this part, I mentioned this formula. R equals the formula. R equals 1/2 times 1 minus B0. What is B0? B. This is B, right? This is a B function. B function B0 corresponds to the constant term. This is B0. B0 is 1. Okay? 1/2 times 1 minus 1. So from that formula, we also get R equal to 0. Yeah. But this tells us, so here. This tells us it's a double root. Yeah. Yeah, case 2, double root. Yeah. All right.
In the case that's not a double root, does that formula just for R still apply?
Yeah. No double root.
You just find one root in that case. I'm saying if it's not a double root, we use that formula.
It must be a quadratic formula.
Okay.
Must be a quadratic formula. Yeah. Yes. Yeah. All right. Yeah. Quadrivial, you always have two roots. Yeah. So single root or double root. Only these two cases. Yeah. All right. Now, next we need to work on. Yeah. So now we get, we need to work on that. Yeah. All right. So that's what we have so far. All right. Sorry. Yeah. Now, to do the work. Yeah. To do the work. Yeah. Now R equal to 0. So we can plug in R equal to 0. Right? Yeah. R equal to 0. All right. Yeah. So here you need to be very patient. Yeah. So R equal to 0. Yeah. So let's see how we get each summation. We can simplify m times m minus 1 am x to the m minus m times m minus 1 am x to the m minus 1. All right, yeah. Plus 3 m times am x to the m, all right, minus, let me do here, minus m times am x to the m minus 1 plus am x to the m, okay, equals 0. Yeah. All right. Yeah, but here you have these m minus 1, m minus 1. Yeah. Yeah. So you want to do substitution. S equals m minus 1, right? Do that substitution. Yeah. So for these two summations, then, so after that substitution, yeah, these three summation we don't need to change, but we need to change to S. Okay, yeah. All right. S equals 0. S minus 1. S minus. Now, m equals 0, s equal to negative 1. See? Summation. All right? Yeah. M equal to s plus 1. Yeah. So that minus 1 s. S times s plus 1. S plus 1. X to the s plus 3 s minus s equal to negative 1. Okay, yeah. So oh sorry, yeah, because m equals s plus 1. S plus 1 x to the s, then the last one plus s equal, oh yeah, too low, yeah, cannot, sorry, negative 1, right? Yeah. So you should be very careful when you work. Oh, sorry. This one, we do not use substitution, remember? Yeah. We only do substitution on these two summations. We don't do substitution on, these three. Yeah? Okay? Yeah, we just switch to S. So we don't have negative 1. AS, XS. Yeah. Equals 0. All right. Yeah. Okay. Yeah. All right. Then, what's next? Okay. Yeah. All right. So here, there is a step. Now, because the starting point, these two summations, s equals -1. Okay? S equals to -1. But think about, when s equals to -1, the first term is 0, right? S -1, this term also 0, right? That's -1. So that means, can you see, because when s equals to -1, that term has no contribution. Yeah, because it's 0, right? Coefficient is 0. Coefficient, these two terms in their summations have no contribution. Okay? Do you think we can change it to 0? Because s equals to -1 has 0 contribution, right? We throw it away. We throw away 0 term. Is that okay? We throw away 0 term. Okay? Here, can we change to 0? Because we throw away 0. No. The 1 we throw away, it's 0, right? No? Yeah. Exponent, don't worry, because the coefficient is 0. The whole thing is 0, right? If the coefficient is 0, the whole term is 0, right? Yeah? Then, remove it. We remove the 0 term. No loss, right? Yeah? So we can comfortably simplify. We call it simplification. Because the -1, no contribution. Okay? All right. After that, because all starting point the same from 0, then we can add all these terms up, right? We can add up all of them. Okay? Directly. Yeah? Because they have the same starting point, same end point, everywhere the same. So we can do the direct addition, right? Yeah. All right. Yeah. So now let's add them. Yeah. So I don't know if I have enough space. Yeah. Let me use this space. Try to find. Okay. Yeah. All right. S times S minus 1. Yeah. S part. Okay. Plus 3S. Right? Yeah. Because here I want to look at the coefficient of AS. Yeah. Coefficient of AS plus 1. Right? Yeah. This whole thing we need to multiply AS minus, okay, S times S plus 1 plus S plus 1, right? Is that, yeah? Okay? All right. Now, yeah, with that, we simplified here, okay? Yeah. Let's do further simplification here. Yeah. So here we need to be very, very careful, all right? This one, can you see, yeah, because S squared, that is, yeah, so we calculate here. S squared minus S plus 3S plus 1, right? Yeah. Expansion, yeah. Then after cancellation, x squared plus 2s plus 1, right? Is it 1s plus 1 squared? Yeah. So the first one becomes s plus 1 squared times as minus. The second minus, factor out s plus square, s plus 1. You inside s plus 1, you also have s plus 1 square, right? S plus 1. equals 0. Okay? All right. Can you cancel out? Cancel out? Yeah. Because it's not 0, right? Yeah. S greater or equal to 0. So we can cancel out. Then you have S plus 1 equals AS. Starting from 0, right? So S equal to 0, dot, dot, dot. Okay? So same coefficient. Okay? Yeah. A0. Yeah. All the same coefficient. Then, remember, what is our y1? Y1 function equals x to the r. X to the r, r is 0, right? R is 0. Inside A0 plus A1, A1 also the same as A0, right? Yeah. A2 all the way. All the A coefficient equal to A0, right? Square. Okay? Then, yeah, is it? Yeah, if we take, yeah, so here, yeah, very messy. If we factor out A0, is it inside just geometric series? Is it inside just geometric series? Right? Yeah? The geometric series, we know, it is 1 over 1 minus x. Yeah. So this is our y, yeah, because our y1, we do not need to contain x, A0, okay? So y1, we just need one solution, okay? So 1 over 1 minus x, that is our y1. Okay? Yeah? Yeah. It's a nice function. Yeah. It happens to be a nice function. Because in general, you cannot expect you have a nice function. Yeah. But for this example, yeah. So to make your life easier, so you have a nice function. All right? Yeah? All right. Let's move to the second. Yeah. We just find the first solution. We need to find the second solution. Yeah. All right. Yeah, here, yeah. This part we did in the previous slide. So I leave this space for calculation. Yeah. But we completed. So yeah. All right. Yeah. All these things. Right. Yeah, we did it now, right? Yeah. All this S we already did. Yeah. So I didn't use. Yeah. Yeah. Actually. Yeah. See. Yeah. Y1. So we are here. Okay. Yeah. I use one slide. I leave a lot of space. I try to do the calculation. But now we're already here, right? Y1. Geometric series 1 over 1 minus x. Yeah. It's a nice function. Okay. Nice function. Yeah. Yeah. All right. The next question is, we need to find the y2 function. Okay. Y2 function, here we are in case 2, right? So this is the case 2. In the case 2, based on the Frobenius theorem, there is a case 2 formula. Yeah? Solution 2 for the case 2, double root. So by the Frobenius theorem, the case 2, y2 solution should have this form. Should have that form. Okay? All right. Yeah. But, although you can plug in, do the calculation, but it could be very complicated. Yeah. Very complicated. Yeah. But our textbook uses one simple way to get around direct calculation. So here I talk about that. Remember, we learned the method before. So here we have a second order ODE, right? This is second order ODE. Yeah. In our module 2, we learned the method. If you find first solution, is there a special method you can find a second solution? There is a method, right? We call it, variation of parameters, right? Reduction of order, remember? Reduction of order by variation parameter. So your y2, you make your y2 function as y1 function times u function, undetermined u function. Then you calculate that u function. Yeah. the U function has a first order ODE. Yeah. So our textbook used that, reduction of order method to determine that Y2 function. Okay? Yeah. So in that way, you get around this, direct calculation. Okay? Yeah? All right. Because think about here, I want to let you know under what situation we can use this reduction of order, right? Yeah. Because when our y1 function is a nice function, when our y function is, this is a simple, nice function, right? In this situation, we can use this reduction of order method. But if y1 function, think about if your y1 function is a complicated, is a power series function, can you still do it? Right? It will be very messy if you use this reduction order. So messy. Okay? How can you determine that U function? Because your y function, it's so many terms. Very hard to determine your U function. So only when your y function is a simple function, then you can use it this way. Yeah. But in your homework, I try to find the question, your y1 function happens to be a simple function. So you can use this reduction of order to get around it. Yeah. But in the final, I will choose one question. Your y1 function is a power series, so you cannot get around it. You have to use this way. Okay? You have to use this way. All right. Yeah. Now, last we have a few minutes. Let's do case 3. Similar. Case 3 similar to case 2. Yeah. Same idea, but we just do things slightly different. Yeah. So here, let me jump to case 3. Yeah. Because after we have the experience of case 2 there, case 3 is not that hard. Okay? Yeah. So, pretty much follow the same path. Yeah, same path. All right. Yeah. So, but let's complete this example. So we complete this whole part B today. Yeah. All right. Solution. Yeah. Extended. We use this form. Yeah. Then, yeah. In order to take derivative, we like to put x to the r inside. Yeah. Multiply through inside. Okay. Yeah. In that way, the derivative representation, very simple. Yeah. Second derivative representation, also pretty simple. Okay? Yeah. Then, we need to plug in. But before we plug in, let's write terms separately. Yeah. Let's write, just the y double prime part in two separate terms. Yeah. Yeah. All right. Then we can, use our power series representation for each term. Okay? Yeah, so 4 terms. Yeah. 4 terms, then the next step. What should we do next? Yeah. You compare the general term, right? So each summation, you compare the general term. These 4 general terms. You can see this summation has the odd one, right? It's the odd one, yeah, because it's different from the other 3. That means you should use the substitution m minus 1, right? Yeah, because the r part, all of them, they have the same r. So our substitution, we do not include the r, okay? Yeah, s equals r, m minus 1. All right, there, so you move to s. Okay, all right. The other just replace m by s directly. The other 3 summations. All right. Yeah. Then you need to get the initial equation, right? Initial equation. All right. Initial equation. Yeah. Here the question: how to get initial equation? Yeah. next question. How to get initial equation? Simple. Yeah. Look at the lowest degree term. Which term has the lowest degree? Yes. The second one corresponding s minus 1. Yeah. S minus 1. This one has the lowest degree. So the coefficient of this term must be 0. That's the initial equation. Okay? All right? So, yeah. So the second one, initial, but yeah. Right. So here I already calculated the final result. But for the initial equation, yeah, we just calculate s equal to 1. You plug in s equal to 1. Yeah, let's plug in s equal to -1. Plug in, okay? Plug in, so we get a negative 1. So r times r minus 1 a 0 equal to 0, right? That's the initial equation, okay? But the a0 we do not treat as a, we treat it as a non-zero number, so we can cross out. Then this equation has two roots, 0, 1 and 0, right? Yeah. So the initial equation like that, R2, R2, okay? Remember, yeah, only two roots, 0 and 1. But why we make R1 1, R2 0, not R1 0, R2. Remember, our case 3, we require R1 greater than R2. Okay? The difference, R1 minus R2, should be positive. Yeah. That's why we make R1 as 1, R2 as 0. Okay. Yeah. Then the summation part after simplification, we can get that. That's the summation part. Okay? All right. Yeah. Then let's move to the next step to calculate Y1 solution. Next step. All right. R1 equals 1 for Y1 solution. All right? Yeah. So that's the, we need to derive the recurrence relation from this equation. Yeah. This general equation. So here, s equal to -1. Can we eliminate it? Can we make it s equal to 0? Lucas?
I know the answer is yeah, but I don't
Yeah.
know why.
Yes, why? Remember, it corresponds to initial equation. Yeah? Initial equation equal to 0, right? Yeah, that term must be 0. Okay? Yeah?
So if it's 0, and then next, if you add 1, it would still be 0. Or you go to the next term.
Yeah, next term. Yeah, because no contribution. This 0 term has no contribution. We can take it away. Yeah. All right. Then, in that way, so we start from 0. Okay? Yeah. -1 is gone. Okay. You don't worry about the -1 case. Yeah, it's gone. Okay. All right. So then, because r equal to 0, r equal to 1. So you plug in r equal to 1. Okay. Yeah. Then, next you can find a recurrence relation. This is the recurrence relation. Yeah. So, yeah. Yeah. Pretty straightforward. Yeah. Do division. Yeah. Yeah. Vanishing property, right? Then, do division. Yeah. For this recurrenzation for s starting from 0, consecutive integers starting from 0. Okay? All right. Now, let's plug in. Okay? S equal to 0. Yeah. So here. Yeah. That's why. S equal to 0. Yeah. Sorry. Yeah. You plug in. Yeah. A1. Yeah. S equal to 0. Equal to 0, right? Yeah. Because when s equal to 0, the whole thing is 0. So A1 equal to 0. If A1 equal to 0, can you see A2 also 0? Because when you calculate A2 something multiply A1. If you see A2 is 0, can you get A3 0? Okay, all the way to the end. All the way to the end. All 0, right? Yeah. So then, but you start from A1. But A0 is not 0, right? A0 is not 0, right? Yeah? Only non-zero coefficient is A0. Okay? All the remaining coefficient, all 0. Okay? Now you go back to here. Yeah. So y1, y1 equals x to the r equal to 0. So it's gone. Okay? So you only have A0. Right? Yeah? You only have A0. Yeah. So is it that y1 equals 1? That's strange, right? That's strange. Yeah? Oh, sorry. Yeah, sorry. R not equal to 0, right? R1 is 1. Yeah, I got contradiction. Okay, now x to the 1 times A0, but our A0, because that constant we take out. So our y1 function equals x. That's the solution. Yeah. So y1 is this a nice solution? Nice one, y2, can we use the reduction of order? Yeah, we don't use power series. So this one, we also use a reduction of order method. Yeah. All right, we run out of time, so let me stop right here. Yeah. So we finish this topic. Yeah. Part B. Yeah.
Thank you, Professor.
You're welcome. Yeah. Mm-hmm. All right, see you next week. Yeah. Yes, a lot of practice. Yeah, but if I give you this kind of question, it should be okay, right? Yeah, no that messy calculation.